Our final speaker in today's session is Kamran Vakili.
Thank you. Thank you all for sticking around until the end of the session. My talk's going to be a little bit of a change of pace from some of the very brilliant and fascinating presentations that preceded it in the session. I'm going to be presenting a very simple toy model of Planck-scale bits, really just a counting argument that seems to yield the Heisenberg uncertainty boundary and the black hole boundary inevitably and symmetrically as thermodynamically enforced information capacity limits. So John Wheeler famously coined the phrase "it from bit," expressing the view that when thinking about reality at the fundamental level, particularly at the overlap of quantum and gravitational physics, it behooves us to think in terms of information. And that perspective has informed some very consequential and well-known results, obviously black hole entropy, holographic boundary entropy, and more recent proposals for an entropic origin of gravity itself. So in that spirit, I'm going to start by talking about some of the assumptions of the model, including a basic proposal for the structure of fundamental bits at the Planck scale. Counting these bits will lead us to an entropy, which we'll leverage to model measurement via some elementary thermodynamics. And what we'll find is that the Heisenberg Uncertainty Principle and the Schwarzschild formula for the radius of a black hole will emerge naturally and symmetrically as sort of two sides of the same coin as, again, thermodynamically enforced measurement constraints. And finally, we'll relate the growth of these bits to sort of universal quantities to make a prediction for the cosmological constant. So our system of bits is going to be characterized by two quantities, an energy and a length. So if we have just one bit, we can argue that the smallest irreducible unit of information is going to be a single value of energy coupled with a single value of length. These two quantities, loosely speaking, conjugate variables, thus become unified at the fundamental scale in their cooperative role in creating information. We're going to impose Planck-scale quantization so that the total energy and the total size of our system are quantized in integer units of their respective Planck quantities. And so if we imagine a two-dimensional phase space of energy versus length, what we're essentially arguing for is to articulate the otherwise formless space with grid points so that we can sort of meaningfully perform measurements, where each point in the grid will be one bit. So there's one Planck particle, one bit. If we have two quanta of energy and length, we're going to argue that we span a space of 4 bits. For 3 quanta, it's going to be 9 bits. And in general, n quanta will be corresponding to n squared bits. That's sort of the basic assumption of the model. And I've called it S here to make the connection with entropy, because these bits are going to be the microscopic degrees of freedom of our system. So how can we use this to perform a measurement? Or what does a measurement even mean in this context? So let's talk about measuring a small energy, which I've called tau here, less than the Planck energy. So the Planck energy is a mass, is 22 micrograms. We're talking about electrons and atoms, sort of quantum stuff. So to measure this, one way to do it would be to have an energy in our measuring apparatus that we can tune to match the measured quantity. And when the match occurs, we can say that the measurement has been performed. So we can't use the total energy of our apparatus because it's too big. It's n times the Planck energy. But we have n squared bits. So if we think of the average energy per bit, that's going to be the Planck energy divided by n. So in principle, for a sufficiently large bit system, we can match an arbitrarily small tau. So let's call the difference between our average energy per bit and tau little f. And when little f is 0, that's when the two are equal, and we can say that a measurement has been performed. But remember, we needed n squared bits to accomplish this. So we can also ask what the global energy difference is for the entire system. So here I've kind of just drawn schematically the bits as buckets, showing the average energy in tau and the difference. So if we want to see what's going on globally, we have to project up from 1 bit to all n squared bits, and that's kind of what I mean by Planck scale as microscope. So we just multiply through by n squared. We get what I call big F here, equal to the Planck energy times n minus tau times n squared. Now this is starting to look a little bit like a free energy. EPN is the total energy of our bit system, kind of by assumption. We talked about n squared being the count of the number of bits, or kind of like the entropy. So if we allow ourselves to think of tau as a temperature, then we can sort of treat this as a free energy and see what happens. So here I'm plotting our little f, which just decreases monotonically as we increase n until we reach the point where EP over n equals tau, for the measurement point. But the global free energy, or the global f, has a little more structure. It shares this equilibrium value, but it also has another equilibrium at 0. And there's a turning point in between. So I call a bit growth threshold. Because if you're less than that, you're going to be able to reduce the free energy by reducing n, by reducing the number of bits, essentially collapsing your bit system to 0. If you want to get that measurement, you have to be to the right side of the curve, so that it's thermodynamically favorable to add bits to your system until you can perform the measurement. So that's simple to find. We just take a derivative, set it less than or equal to 0 to access the right side of the curve over here. And if we substitute the total size of our bit system using our quantization condition for n, we arrive at L tau has to be greater than or equal to h bar c over 2. And that's essentially an expression of the Heisenberg Uncertainty Principle. What it says is that the size of our system, our measurement apparatus, has to be at least as large as h bar c over 2 tau to be able to perform the measurement. If we're less than that, then we are on this side of the curve, and essentially our bit system collapses. There's no more bits. And it's sort of suggestive in a way of maybe the reason for the uncertainty of the uncertainty principle, in the sense that there's simply no bits there to encode information in the context of this model. Now, what about a large energy? Something bigger than 22 micrograms, so a baseball or a galaxy or something like that. How can we measure that? Well, we can do the same thing. Now we can just directly compare that to the total energy of our system, NEP. So that's, again, our global energy difference, big F. And just like before, except we're going to go the opposite direction. Now, instead of projecting from one bit to all the bits, we're going to project from all the bits down to one bit, see what's going on at the per bit level. That's what I mean by the Planck-scale as telescope. So again, just drawing out the bits, and now we're going to divide through by n squared and see what happens. So we're going to recover the little f, the local energy difference per bit, and it's going to be EP over n minus h over n squared. Now again, if you think of EP over n as sort of the energy per bit, the total energy within each bit, and if h, you allow yourselves to think of it as a heat, that's the heat distributed across all the bits. This is kind of like the total energy per bit minus the heat per bit, so like a local free energy per bit. So again, drawing those here. On this scale, the global free energy looks very vertical, but it's really just a straight line with a finite slope. But there's more structure again in the local free energy, and there's a turning point below which the system will collapse and above which it can grow. So we can just do what we did before, take the derivative to access the growth side of the curve, substitute the size of our bit system using our quantization condition, and we arrive at L must be greater than or equal to 2gh over c4, or written as a mass just using mc squared, 2g m sub h over c squared. And that is the well-known Schwarzschild formula for the radius of a black hole, again emerging here as a thermodynamic measurement constraint for our bit system in order to have growing bits to perform measurements. So the Heisenberg Uncertainty Principle and the Schwarzschild black hole emerge symmetrically in this model, two sides of the same coin. And it, again, in a sense, it makes sense because they are both limits on what can be known in nature, right? You can't know what's inside the Heisenberg bubble, nor can you know what's inside the Schwarzschild bubble. And the symmetry I've kind of, on the right side there, I plotted these on a log-log scale, and I apologize for the quality of the graphs there, but you can see the symmetry around n equals 1, which is exactly the Planck scale, right? N equals 1 is one Planck particle. So at low energy, here at the bottom, the Heisenberg boundary dominates, right? It's the larger of the two, and the black hole is hidden behind it. As you add energy to the system, the measured quantity, you shrink that Heisenberg boundary. You grow the black hole boundary until they cross near the Planck scale, and as you continue to add energy, the black hole takes over and dominates. The Heisenberg boundary is hidden behind it. So in this model, the Heisenberg Uncertainty Principle is a global constraint on the bitwise measurement of small energies And the Schwarzschild black hole is a bitwise constraint on the global measurement of large energies. And finally, if we can go back to our global free energy, just write it in terms of the size of our system using our quantization condition, we can do a little more elementary thermodynamics and just ask, with a lot of hand waving, what the pressure might be. Just take the negative derivative of the free energy with respect to volume. We can maybe assume 3 dimensions and isotropy to rewrite the volume derivative. And then we plug in our expression to get 2 terms for the pressure, one that's a positive term that depends on tau, and a negative pressure term that only depends on L, the system size. Negative pressure of space-time has been related to the cosmological constant by this well-known expression. So in principle, we can relate these two, solve for the cosmological constant in this model to get 2 divided by L squared, where L is the total size of our system. And if that system is the universe, we can plug in the co-moving radius, 4.4 times 10 to the 26, to get a model prediction of 10 to the minus 53 inverse meters squared for the cosmological constant, which compares favorably with the observed value of 10 to the minus 52 within an order of magnitude, which is a little striking just given, again, the extreme simplicity of this model and the fact that we're talking about the thermodynamic behavior of bits, of microscopic Planck-scale bits. So in summary, our bit system is characterized by energy and length. That's sort of the fundamental unit of information. This n-squared form of the entropy is a key. And the result is this unified model of Heisenberg uncertainty and black hole boundaries as symmetric, thermodynamically enforced measurement constraints. And last but not least, the bit growth rate, at least expressed as a pressure, seems to give a reasonable approximation to the observed value for the cosmological constant. Thank you.
Thank you. We have time for one question.
From what I've seen, impressive, but I had a question as I believe you can get the Heisenberg Uncertainty Principle just from the idea of the wave-particle duality. Mm-hmm. I was wondering of how does your model relate wave-particle duality?
Well, that may be a step past anything that is in the scope of this model directly. This is really, like I said at the beginning, just sort of a counting argument. So I'd have to think about how you might be able to get to something like, well, I'll tell you this. So we have a free energy. You could, in principle, make a partition function. So if I go back to my free energy expression here, so that would be in the exponential, right? You would exponentiate that to get a partition function, something like that. And if you maybe allow n to be complex or something, you would be getting wave-like terms in the partition function. And that might be interesting because a partition function is a statistical weighting function, right, for sort of statistical mechanical processes. And this could maybe make the connection to the Feynman path integral, right, which is also kind of like a weighting function. And again, if you used n complex, you might get wave-like properties there. Mm-hmm. That's probably the best I can do in terms of an answer.
So would this be related to the idea of hidden variables?
I'm not sure how that would relate. I'd have to think about it.
Okay, thank you.
Thank you for the question.
Thank you. Let's thank our speaker again. Thank you. We've reached the end of the session today, so I'd like to thank you, the audience, and a big thank you to our excellent speakers. One more round of applause.